Now let's do another problem. In this case, it's the same question. We want to know if this function from R2 to R is continuous or differentiable, maybe. And we have here, the function is given by this formula when x and y are not zero. And at 0, 0, we define it as 0. So we have xy divided by square root of 3x squared plus y squared. So let's see if f is continuous or differentiable or what. Now, first thing, you could try different paths. Okay, you can see here the net power in the numerator is like a square, and in the denominator is, you see, we have squares, but we have a square root. So the same trick that we applied in the previous video will not work here. And if you try several paths, you may come to the conclusion that either it's very tricky or it should be continuous because you keep getting the same limits in any paths you try. So we can try to show that it's continuous. Remember, the difficulty here is that you need to show that no matter what path you pick, it will always get the same limit. So let's do that. Let's take, because we want the limit to be 0, okay, we can just see the absolute value, okay, because the absolute value from one side is already bigger or equal than 0. So if we can estimate this by something that goes to 0, we are done. Okay, so that's our goal. This is equal to xy divided by square root of 3x squared plus y squared. Okay, and here, well, this is our standard procedure, right? So 3x squared plus y squared is bigger or equal than, let's say, y squared, doesn't matter. We could take 3x squared, but just to get rid of the 3. So this is absolute value of x times absolute value of y divided by the square root of y squared, which is the absolute value of y. And these two cancel, and then the x that is left when x, y go to 0, 0 converges to 0. So we are good to go. So f is continuous at 0. Okay, so we are, that part is good. Now, differentiability. We are going to do it in a way that is more complicated than it needs to be because we don't know enough yet. But in a couple of videos, it will be much easier than the process we are going to follow now. Okay, what does the definition say? The definition says f differentiable at xy equals 0, 0 if and only if there exists a matrix A, well, in this case, a vector from R2 to R, such that the limit, right, and we need to write f of, let's write x plus 8 minus f of x minus a8, okay, divided, this goes in modulus, divided by the modulus of 8, and this has to be 0. As 8 tends to 0. Okay, this is what the definition says. Now, at this point, we don't have a guess for A, but in a couple videos, we will be able to start this problem having a guess of what A should be if the function is differentiable at all. And that will help a lot because right now we don't know. But once we can just plug in a guess, the problem becomes much easier. So let's start. So here, when I wrote this point x, this is the problem where the point where I want to check differentiability. So this is actually 0, 0. Okay. I know f of 0 is 0, so this I can already get rid of it. And then this h, okay, is the is some point h1, h2 in R2. Okay, so let's write this down carefully. Now the other thing that I was saying I don't know is A. So because I don't know A, but I know is a linear mapping from R2 to R, I can write its matrix, right? Which is, let's call it AB. Okay, it has one row, two columns, and it has two values, A and B, two entries that I don't know yet. So that I will need to deal with later. That's part of the difficulty right now. So let me rewrite the whole thing. H1, H2 tends to 0, 0. And here, f of h, let's copy paste. This is f of h, but of course I need to write h1, h2, and this is h1 square, h2 square, minus 0, minus, and then this is a h1 minus a, minus b h2. And then here I divide by square root of h1 square plus h2 square. And I want to know if this is 0. Okay, but again, I don't know A and B yet, and that's a problem. But it will not be a problem for long because we can actually guess what are A and B. Okay, to guess A and B, what we are going to do, we are going to choose appropriate paths. What are appropriate paths? So it's very easy. We are going to approach from the coordinate axis. So take h1 equal t, h2 equals 0. Okay, let's take this one first. When I do this, let me copy paste this little sweetheart. All right, and here, because h2 is 0, this goes right away, this goes right away, this goes right away. Okay, and then this here is t. And this is square root of t squared. So what I get here is the limit as t tends to 0 of absolute value of a, absolute value of t divided by absolute value of t, these two go, and I need this to be equal to 0. This is equal to a, right? But this function will only be differentiable if this limit in this particular path is 0, because that's what we are aiming for. Okay, sorry about that. So anything different from 0 destroys differentiability. So if f is to be differentiable, a must be 0. Let's write must here. A must be 0. Okay, there is no other choice. So we have already guessed one. To guess the other one, we are going to take the other axis. This you do. It's the same computation. What we get is that b must be 0. Okay, so this is actually very good, because before we didn't know neither A nor B, but now we do. So there is a lot more than we can say here. Copy paste that limit that we need to see if it's 0 or not. Okay, so now this one and this one go, and we can work to the end game. H1, H2 to 0, 0. So this is how to write it. Let's put everything on the same fraction. So this is 3h1 squared plus h2 squared square root of h1 squared plus h2 squared. And see what happens here. What is the net power in the numerator is like basically n square, because there are two, h1 and h2. And in the denominator, we have this here is like a power of 1, and this is also like a power of 1 because it's a square root of a square. So we can apply that trick that we used in the previous video to see that this limit does not exist. Okay, so take the path h1 equals h2 equal t. So this is the limit as t tends to 0, t squared divided by the square root of 4 t squared, square root of t squared. So that is the limit as t tends to 0, t squared divided by 2. So I have is absolute value of t times itself, that's t squared. So this is 1/2 different from 0. So it's not, well, actually it should be a happy face because we are done, right? This means that the function is not differentiable. F not differentiable at 0, 0. Okay, because we found one path where the definition of differential just won't work. So just to recall, this exercise was more difficult than it needs to be because we started not knowing what the differential could possibly be if it existed. Okay, but then once we guessed it, it became easier. We just plugged the differential in, and then it was just computing a limit. And then the limit is a question of trying a few paths. If it looks like it's going to work, then we need to do a proof. If we happen to find a path where it doesn't work, that's it. Now, you may be wondering, how does this look geometrically? So I plotted the function for you. Here we have it. And when you see this function, the function looks clearly continuous at 0. That's what we got. But if you look at the function from this profile, you see it looks like the absolute value of x, maybe with a different slope, but it's a corner. Corners are bad for differentiability. And that's precisely, you see, the path that we are following there is the path where x and y are equal. Okay. So that's precisely the path where it has that point that we detected with that limit. So you can see, I mean, if you look at this graph, the guess should be like, this can't be differentiable at 0 because it has that pinch, that corner.